Welcome to the API Academy video series. You are watching the Introduction to API Security video. By the end of this video, you will be able to explain the unique security risks of APIs, define the users and components within the API security domain, identify typical areas of API vulnerabilities, and summarize best practices for securing APIs. Understanding the risk profile of APIs is vital to protecting your APIs against possible attack. APIs share a lot of characteristics and underlying technologies with traditional websites and applications, and therefore share many of the threats as well. However, APIs are fundamentally different and have a unique risk profile, so we cannot rely on the same security methods and technologies that we use to secure the browser-centric web. Well-designed APIs are, by nature, more transparent than websites. This transparency also exposes the internal structure of the backend systems and client apps on either side of the API, providing clues to vulnerabilities. One of the key considerations that should guide both your API business strategy and your interface architecture is the distinction between public and private APIs. An API can be defined as private or public depending on whether it targets in-house or external developers. A partner API is a hybrid form of the public and private interface models that targets only specific developers. This diagram represents the most typical context of the components and users in the API security domain. There are the APIs, applications that are using the APIs, and a developer portal that publishes and distributes keys for those APIs. And then there are the users involved: the end user using the application, the developer who built the application using the API, and the publisher or administrator of the API. Attack surfaces can occur when there is an interaction between the components or between the users and the components. APIs give client-side developers and potential hackers much more finely grained access into the backend than a typical website or application does. Because APIs shift the granularity boundary from relatively secure internal tiers out to a client application residing on a user's device, the potential attack surface is significantly increased. Therefore, it is advised that you should protect your APIs well. Every year, the number of API breaches increases. It could be happening because there are more and more APIs, but also because API security is often treated as an afterthought. For example, if you have a mobile app with a private API, you might think it's private, therefore automatically secure. However, it is still an API exposed on the web and therefore vulnerable. API breaches can occur anywhere from internet browsers and browser extensions to IoT devices. Here are examples of some of the most common web attacks. Cross-site scripting attacks are a type of injection in which malicious scripts are injected into otherwise trusted websites. An attacker uses a web application to send malicious code, generally in the form of a browser-side script, to a different end user. The denial of service attack is focused on making a resource such as a site, application, or server unavailable for the purpose it was designed. If a service receives a very large number of requests, it may not be available to users. The man-in-the-middle attack intercepts communication between two systems. The attacker splits the original connection into two and acts as a proxy that can read, insert, and modify the data in the intercepted communication. Cross-site request forgery is an attack that forces an end user to execute unwanted actions on a web application in which they are currently authenticated. An attacker may trick the user into executing state-changing requests like transferring funds or changing their email address. An SQL injection attack consists of insertion of an SQL query via the input data from the client to the application. The exploit can read or modify sensitive data from the database. Overflow errors are characterized by the overwriting of memory fragments of processes. Overwriting values of the IP and other registers causes exceptions, segmentation faults, and other errors. The above-mentioned examples can be found with more details at the OWASP website. You can also find the OWASP Top 10 there, which is a standard awareness document for developers and web application security. It represents a broad consensus about the most critical security risks to web applications. In their Top 10 Web Application Security Risks for 2019, unprotected APIs belong under security misconfiguration. There's also a separate Top 10 list for API security in particular. Again, these are the Top 10 for 2019. The lists are updated every year. Let's take a look at some real-life case studies. Snapchat messaging application was a target of an application identity spoofing attack. The hackers were reverse engineering the API that was used by the backend of the Snapchat mobile application and therefore were able to steal users' data. Using an API key retrieved from the official application, they created a fake app where they could control the calls. The API took a phone number as input, so they just made a few million calls using every possible phone number. Successful responses tie those phone numbers to actual accounts, and the attackers could also retrieve additional info like friend lists and images. SQL injection is an incredibly common exploit. Here's a list of high-profile breaches over the span of less than a year. The attack on Verizon consisted of an application identity spoofing, capturing a legitimate user's credential token to make additional illegitimate calls. In this cross-site request forgery attack, the use of a cookie-based authentication was clearly the cause of the vulnerability. The victim signed into their Verizon account and received a session cookie. The users were tricked into clicking an external link to access a malicious website. This caused the cookie to be shared. The malicious page made the browser send an API request to Verizon using the stored cookie. This allowed the attacker to hijack additional private account data of the users. Some owners of Nissan Leaf discovered a vulnerability in their Nissan Leaf iPhone app. They could retrieve data and control some functions of their cars without the app. The request that the phone had issued didn't appear to contain any identity data about the authenticated session. In other words, the user was accessing the API anonymously. Moreover, it was actually possible to access other people's cars by entering the last 5 digits of the VIN number, which they could read off the dashboard of an unattended car. Let's take a look at 4 standard security functions from the API gateway world that are important when it comes to protecting your APIs and mitigating API threats. Rate limiting, message validation, encryption and signing, and access control. Rate limiting is used to prevent denial of service attacks and controls the amount of incoming and outgoing traffic in the network by restricting the number of requests. It is considered a critical element for keeping APIs available for legitimate users. Message validation prevents message-based attacks, including injection. It validates incoming and outgoing messages, and validates requests against a predefined schema after message is received. Encryption and signing prevent spoofing and man-in-the-middle attacks, and can be performed at the transport level or at the message level. Last but not least, there is access control that restricts usage of APIs based on user identity. The authentication question is basically, are you really who you say you are? And the authorization question, are you allowed to access that resource? Going a bit into the history of access control, this is what you would typically deal with in the API world back then. In 2008, APIs were mostly SOAP interfaces, SAML was used for access tokens, and XACML for authorization controls. Today, we are still relying on the same transport layer security, but have introduced OAuth and OpenID Connect to enable delegated authorization and identity token management. OAuth 2 is foundational and extensible, enabling future extensions to fill gaps and support new scenarios. TLS and SSL are cryptographic protocols that help you keep the internet connection and transfer of data secure. Steps to secure connection based on cryptography are: choose a supported cipher suite, use key material such as private key or public certificate, and make sure that the validation model is based on certificate trust. Security through cryptography is a constant arms race, as more complex algorithms and larger key sizes try to hold up against rapidly increasing compute power being leveraged by malicious actors. Cryptography is secure not because it is impossible to crack, but because it is impractical. Brute force approaches to guessing the key material used might take decades or even centuries to succeed. But the computing power used to crack these algorithms continues to get cheaper and more powerful, and occasional breakthroughs in approach reduce the time needed by orders of magnitude. New cryptographic algorithms and increased key sizes extend the time it takes to crack these systems, but also increase the size and complexity of the systems needed to implement them. Here are some historical vulnerabilities related to TLS-SSL protocols that were high-profile enough to get their own names. TLS trust attacks can be divided into three categories: certificate authority vulnerabilities, where a trusted certificate authority can be compromised and can issue malicious certificates. Human vulnerabilities, where browsers can use visual cues such as padlock to indicate security. Visual cues can be impersonated, and of course, people can be fooled. There is also man in the middle, where data sniffed by a proxy server can be sent outside of TLS channel, or a crypto attack on encrypted data can be launched. Let's take a quick look at HTTP access control. HTTP provides an access authentication feature, allows servers to reject unauthorized access and challenge clients, allows clients to transmit credentials, and works with two popular authentication schemes, Basic and Digest. In Basic authentication, username and password are in the request header. Base64 is encoded, not encrypted, and credentials are sent in plain text with every request. As for the Digest authentication, the password is encrypted, and the server can downgrade scheme to Basic. This type of authorization is vulnerable to man-in-the-middle attack. To sum up, here are some best practices to follow when securing your APIs. Make sure that you have a good authentication and authorization system in place for your APIs. Be aware of the security issues according to OWASP. Limit the number of requests and retries that the API accepts within a certain time window. Think about continuous API monitoring and review API access periodically to identify possible issues. Remember that APIs that return too much data are vulnerable. Last but not least, prevent applications from sending error messages with system traces. We've discussed how some of the technologies mentioned in this video have been compromised. Others are simply insufficient for modern scenarios involving multiple parties, access control delegation, and consent management. Because of these various vulnerabilities and limitations, new sets of specifications arose, such as the OAuth framework for authorization and the associated OpenID Connect authentication layer. These will be covered in more detail in other API Academy videos. You've reached the end of the video, Introduction to API Security. You should now be able to explain the unique security risks of APIs, define the users and components within the API security domain, identify typical areas of API vulnerabilities, and summarize best practices for securing APIs. Thank you for watching. We will see you in other installments of the API Academy Learning Series.